Okay, good. Yeah. Yeah, and Osvaldo Simeone, that was my supervisor while I was Kings. This work, this presentation is about the robust Bayesian learning framework that we developed. I was there, and the application of that this framework has on wireless communication problems, in particular, in order to ensure reliability under the learning conditions that characterize these learning scenarios. The presentation will begin with I would say, introduction to what is reliability and what is Bayesian learning, and but this will be very brief. And then we'll see what are the limitations of this framework and why we need to use robust Bayesian learning and to develop such tool for to perform reliable wireless AI. Okay, so this is a motivation slide, which in this case would not be that necessary because I think in these 3 years we have seen that AI has vast application for wireless communication. However, being wireless communication a relatively different field from what computer science is, we have seen that the requirements that AI should provide in wireless communication is different from the one that typically are required in computer science. In particular, we have that the accuracy, which was the only figure of merit, has to be weighted against reliability or calibration, which is the ability of the model to quantify uncertainty about its decision, and robustness, which is the ability of the model being trained over some specific scenario to gracefully adapt to a different one. Reliability is particularly important because it allows wireless communication system that employ AI to be monitored, because whenever a wireless system, a machine learning model becomes bad, it might not be able to understand that it's becoming bad, whereas if it's well calibrated, its confidence becomes low, and then we can trigger some retraining procedure. Calibration is also important because decisions sometimes have some very big implication in decision-making processes, and therefore attaching some confidence level to that decision may be good in those scenarios. So what is calibration? In this talk, we look at discriminative probabilistic models, which are models that can be summarized by a probability over the output space, which we denote as Y, given some input X and some model parameter theta. For example, in neural network, we have the input vector X is mapped through a parametric model into a distribution, in this case, discrete distribution over the classes. And from this schematic model, we can obtain the decision, which is typically obtained by thresholding the output layer and choosing the class with the largest score. But another way but we can also obtain confidence by just taking as a confidence level the score associated to the class with the largest score. For instance, in this case, class 1 is the one with the largest score, and we have that the confidence level associated to that class is 0.4. How then can we assess whether a model is reliable or calibrated? This is easy whenever we have some data that we can validate our model on. And in particular, we have that the model is calibrated whenever this score that is self-reported by the model is close to the accuracy of that model. So for instance, in this case, if the model outputs for a given input X, the class 1, we expect that 20% of the times, the model does the right prediction. And in that case, we have that the accuracy of the model is close to the confidence that the model predicts. And this is a very important thing because if we have low confidence, whenever we make a decision, we can maybe refine the decision or put a human in the loop and do something more intelligent. A problem is that frequentist learning is typically overconfident, or neural network tends to be overconfident. Namely, they make mistakes and they're sure about their mistakes. And this is a problem. Luckily, we have a tool, which is Bayesian learning, that allows to limit at least this limitation of frequentist learning. Bayesian learning deviates from the frequentist learning paradigm because neural networks are not now, the output of learning algorithm is not now parameter theta, but is rather a distribution Q theta over the model parameter. So for instance, if this is a layer of neural network, we have that every weight is described by a distribution. And this distribution, Q theta, encodes the epistemic uncertainty, which is the uncertainty due to the fact that we have limited data whenever we train a model. How do we obtain Bayesian learning? Well, Bayesian learning, again, as frequentist learning, is based on the minimization of a training loss, which in this case is the usual training loss plus an information theoretical regularization term. And the goal of this minimization is to find the distribution Q theta that minimizes these two terms together. The first term intuitively is tells you, okay, we need to minimize the average training loss, finding a parameter, a final distribution of the parameters. But we also have an information theoretic regularizer that tells us that our new belief about the distribution over the model should be not that far from our prior P theta that encodes the prior knowledge about the problem. If we have beta equal to 0, we fall back to the frequentist learning approach, and the output of this minimization is, again, a single model parameter. This criterion is well justified, it doesn't come out of nowhere, but it's justified by Bayesian theory that provides bound on the population loss of Bayesian models. And these bounds typically have this form, which is the average training loss plus this information theoretic regularizer. The question now is, we have seen that previously, frequentist learning, a model is a single parameter, so it's rather easy to understand how we make prediction. We feed this model and we obtain the output. However, in Bayesian learning, we have a distribution over model, and therefore this model itself is not a deterministic entity, but rather a stochastic predictor. How do then we obtain the outputs? We use ensembling, namely for a given input X, we sample this model, let's say a finite number of times, and then we aggregate the outputs and we do the mean output and obtain the final prediction, which in this case is the combination of multiple models. The benefit of this is that, another decision is taken by thresholding this combination of models, and the confidence, again, is the score associated to the largest output. However, differently from the previous case for frequentist learning, since we now combine different models, we somehow account for the disagreement about model. So namely, if we have a lot of uncertainty encoded in this distribution Q theta over the model parameters, we have that this model disagree, and therefore when average, the confidence will reflect better the fact that we're not sure about our predictions. However, Bayesian learning has some, Bayesian learning is theoretically grounded, has many neat mathematical properties. However, these are usually obtained under some ideal condition, and therefore Bayesian learning, whenever it's applied to real problem, somehow has some inherits some limitation due to these design assumptions. The first one that we look at is called modeling specification. So typically, when we commit to a model class, we assume that this class is well representative of the true data generating distribution. However, for instance, in wireless communication, whenever we have devices which are computationally constrained or memory constrained, we cannot, we don't have the luxury of committing to a large model class, and therefore we choose models that are simple. And this clearly is contradictory with the necessity of representing complex phenomena using simple models, and therefore we most of the times fall in the misspecified scenario in which our model class is a rough approximation of the true data generating distribution and the optimal predictor or regressor. So to highlight how Bayesian learning fails in such a situation, let's consider a toy example. Suppose we want to estimate the density of some channel model, let's say a millimeter wave channel model. And we assume that this channel model has two modalities, for instance, one associated to the line of sight and one associated to the non-line of sight conditions. And this is the distribution of the X, which in our case is like H, if you want to use the wireless communication notation. However, since we are now, this is a toy example, so we make a very simplistic assumption and we assume that the data distribution, so the distribution of the channel is unimodal, and therefore we assume a Gaussian likelihood, which is given by a normal distribution, right? What happens if we do Bayesian learning in this case? So what happens if we minimize the objective that I showed you before? Turns out that since the model is misspecified, we cannot actually, we come up with a rough approximation. And even if we do ensembling, and this is the catch, even if we do ensembling, so even if we have the possibility of combining multiple Gaussian distribution, we always come up with a single model distribution. As you can see here, even if we use different beta parameters, and therefore we can like tune one of the knobs that we have seen before in the generalized Bayesian learning rule. If we change the weight of this information theoretical regularizar, we always end up with a single model predictor, which is, as we can see, a very poor approximation of the underlying target distribution. So Bayesian learning, even if he has the potential of combining multiple models and coming up with good predictive uncertainty quantification, if it's carried out under misclassification, yields poor results. So yeah, this is what I just said. So yeah, general Bayesian learning doesn't capture the performance of ensemble predictor, but it just collapsed to a single Gaussian in this case. And the problem is that the average training loss, how it is computed, because if you see the training loss that we try to minimize as the expectation over the model parameters outside the log, outside the loss function. And therefore, we are not really evaluating the loss of the ensemble predictor, but we are rather evaluating the loss of multiple models. So we do combination after computing the loss. And this is very useful computationally speaking, because you just draw a model and evaluate its loss. However, this quantity, whenever the model class is misspecified, is a really bad approximation of the loss of the ensemble predictor. That is the loss that we would obtain if we would take this expectation inside the loss function. So one natural way to deal with that is to replace the loss, the usual loss. And Morningstar proposed the so-called PAC-M Bayesian framework, in which instead of minimizing the loss of a single model parameter randomly sampled from Q, we compute the Monte Carlo average of the model predictor. So for m equal to 1, we go back to the original case in which the loss is the log loss of a single model, but whenever n is greater than 1, we actually compute the ensemble predictor for m model, and then minimize this new m sample free energy metric. And again, this can be justified by Bayes' theory, and you can obtain some theoretical properties. But what's interesting is that now, if we go back to the previous scenario, we have that now this is 5-1 robust Bayesian learning, meaning that we take 5 models whenever we compute the sample averages. You can see that now this distribution is better. I mean, it looks better. We have 2 modes at least, and this is a better approximation of the target distribution for sure. Yes, sure.
When you compute the average there, so all the same models have the same weight, right? You don't differentiate more.
No. Indeed, when you the draw with the 1 to the m, so when you do this one. Okay, this should be a vector. Sorry.
No. Here you write 1 over n was the sum for I equal to 1 to n, right? So yeah, in the last one.
This one, yeah. Okay.
There are basically complete the average of the probability distribution.
Exactly.
In the same way to all models.
No.
Yeah.
No, theta I mean I is different. So
I is different, but the weights that
okay. I mean the weighted average you mean, not the weights of the model. Okay. Yes. This is yes. Because indeed, I mean, yeah, this makes sense because you want to approximate the expectation. So you sample from Q, right?
Yeah.
So if you sample from Q by the large numbers, if you do the unweighted average, you convert to the mean of that quantity. So you don't need to do any weighting here. If you have a skew distribution, then you do, you correct if you have a mismatch between what you can sample and what you want to approximate, then weighting it makes sense because But in this case, you have access to Q, and then you just draw and average as we did here.
I would assume that if you don't have a mismatch on the data size,
if you don't have a mismatch, yeah, if you have Q degenerating to some, if you have Q which is degenerate, yes, yeah, that's okay. set, yeah. So we see that with 5.1 robust Bayesian is able to take all misclassification. However, there is another important limitation of Bayesian learning, which is the presence of outliers. So what are outliers? Outliers are data points that do not follow the same distribution of the test data. So errors due, for instance, to human labeling, like this case, peacock being labeled as an automobile, or in wireless communication system, interference might be an outlier, or whenever you have crowdsourced data, like for instance, I will see later when we do like RSSI localization, we may have devices that report trash instead of real measurements. In those cases, you have outliers in your training data set. We use this standard model but which is very general indeed, but yet very simple to model outliers. We have our in-distribution measure, which is PX, what we want to approximate. And then we have an auto-distribution measure, which is the one that is used to model the presence of outliers. And you have this parameter epsilon that tells you the contamination ratio in the measure P tilde that you actually sample from. So now your distribution is not the real distribution, the one you want to approximate, but is something else which is contaminated by outliers. And now let's go back and let's see how this PAC-M, the Bayesian learning framework that was able to take on misclassification, reacts in case you have outliers. So now we have an outlier, this red cross, and you can see that the mask covering behavior of the robust Bayesian learning now has some serious drawbacks, because the mask covering behavior now makes this predictive distribution to put a lot of weight on the outlier, which is something which we don't want to model. We want to filter out. But we see that indeed the resulting model highlights in its predictions. Why this is the case? Because the Bayesian learning is typically based on log losses, and the log loss is particularly delicate because it's an unbounded function. So for instance, if you have a predictive model that I should have put a theta here, so you have a discriminative model that assign a probability y given an input x, and you have that the new output you see is very unlikely, so it has a very low probability. Then the log loss, the negative log loss, gives him a very large surprise or a very large weight. And therefore, whenever you have outliers and you learn by the log loss, if you convert to something that you think makes sense, but then you see something else that is anomalous, your model is heavily affected by that because of this nature of the log loss. So what we propose is to go beyond the log loss and use the T log loss, which is a generalized logarithm function. This is the formula for the log T loss, and that we have that T has to be between 0 and 1, even though it can be extended to the whole real line. But for T equal to 1, for T going towards 1, we have that the log loss goes back to the standard log loss. However, so we have that becomes the red line here. However, if we decrease T, we have that the log loss becomes bounded by this quantity here, and therefore the T log loss for T less than 1 might be able indeed to limit the effect of outliers. And this is okay. So this is the theoretical underpinning to make our solution robust. And therefore, what we propose in the end is to combine the previous criterion, the multi-sample criterion, the PAC-M criterion, with this new log T loss. And we end up with a very similar learning criterion, which we call MT robust Bayesian learning, because now this criterion has two knobs that we can turn. We have one knob, which is the T of the log T loss, which determines the robustness of the model to outliers. And then we have the number M, which is an integer in this case, and this is the number of constitute models that we use to build the ensemble and compute the performance of the ensemble model. Okay, now we can go back to our example and see what happens with this MT robust Bayesian learning rule. Again, the blue line was the one that we would have obtained with the log loss. Now, if we decrease T and we become more and more robust to outlier, we see that we retain the multimodal behavior of the predicted distribution, but we heavily reduce the effect of the outlier in the final predicted distribution. And therefore, this criterion, I mean, at least in the third example, and as we'll see later in the real examples, is able to counteract both misclassification and the presence of outliers, and obtain good predictive uncertainty quantification, even in these scenarios. Okay, now let's go to the wireless communication application. Clearly, let me say a few words. For this criterion, we have theoretical analysis, which we show that we can recover all the Bayesian guarantees, and we can also carry out some influence function analysis of this criterion, showing that theoretically quantifying the influence of outliers in the output distribution. Namely, we do a sort of a sensitivity analysis to show that indeed using the log T loss makes everything more robust. Rather than stopping to this thought example, we provide some more formal. Okay, now why this is important in wireless? This is important because in wireless we have, as I said before, training data which is affected by exogenous noise. So, for instance, interference or malicious reporting. Namely, we have outliers, and in wireless communication, typically we want to make ultra reliable and low latency decisions. So, lightweight models must be employed in order to make everything faster and not consume a lot of energy. And therefore, likely we have misspecified model classes. Now we give some application of robust Bayesian learning to wireless system. We begin with automatic modulation classification. This is a problem that entails finding the modulation of a signal given a capture one. So a device is somewhere in the network, and this is very important in cognitive radius. As the device in the network is sense the spectrum, and you receive a signal, and you want to understand what is the modulation of the received signal. Actually, not the base station, sorry, the base station. The base station received the modulated signal from the device, and it has to understand what was the modulation used by that device. But now suppose that we have two devices that have a collision. In that case, this is a non-informative example because the very same trace can be, when the two messages are combined over the air, can be assigned to two different labels. So this is a non-informative example that cannot be uniquely assigned to nor one or the other modulation class. So this, we say that these are the outliers. So what we do then is to use some standard de facto data set by Timo Shia and Jakob, and we train a neural network classifier to classify the received signal. We train this neural network using the Bayesian framework, and during training, we consider 30% of the sample affected by this kind of interference with two overlapping signals. And then we test the model under the normal condition, which is the condition in which these devices, the received signal is a single modulated class. So training is carried out in presence of outlier, testing is done on a clean data set, because this is when we want to obtain good performance. And we measure, as I said before, the final model in terms of the performance of the final model in terms of accuracy, but also calibration, because we said this is an important metric. And what we show is that we show the following. Let me explain this. So we have T here. So whenever we move on the x-axis for any criterion that has the log T loss, we change the T parameter of the log T loss. In the upper plot, we have the accuracy, so not easy metric to understand. And this we have this DCD, which is the expected calibration error, which tells you is an error, so the lower the better, and tells you how well calibrated is the model. So we have the frequencies in gray. We have the 1T robust Bayesian learning, which is the case in which we use only the log T loss, and then we have the 4T robust Bayesian learning, in which we use the log T loss and the multi-sample criterion to approximate the ensemble performance. And what we see is that for T equal to 1, the performance of the model is heavily affected, especially in the Bayesian setting, with only one ensemble model, is heavily affected by the presence of outliers. However, as we decrease T, the accuracy of the model increases and eventually surpass the frequencies one. Coming to the accuracy, we see a similar behavior. The accuracy, the calibration the calibration of the model, which is trained for t equal to 1, so in a non-robust manner, is heavily affected. And this performance increases, become better, as we decrease t up to a certain value. And once again, we can see that the red line, which is the one that does not take advantage of multi-sample bounds, performs worse than the one that takes advantage of multi-sample bounds. So in short, our framework, which combines multi-sample bounds and t-log losses, is able to counteract both and provide the best performance. Well, now we can go to another scenario, which is RSSI-based localization. In this problem, we have a device that sends, let me see if I change the image. Yes. So we have a device which is positioned at location Y. This is what you want to predict. And you have base station that measure the strength of the received signal, of a reference signal, and build our RSSI vector, so a received signal strength indicator vector that combines the measurement from the old base station. And what we want to do is to, based on this vector here, locate the device and namely estimate Y. In this case, what could be outliers? So the RSSI-based localization, in order to scale, has to make use of crowdsourcing, and therefore we cannot really neglect the possibility of having malicious devices or devices which very low self-reporting localization capabilities that instead of reporting the true location, report some other location which is completely off. And this, again, is an outlier because we don't want to model this. This is an anomalous data point that we want to be able to discard from our final model. Again, we consider training scenarios in which, we consider training scenario in which an epsilon fraction of the reported location are random. So modeling malicious or inaccurate reporting. And I would like to first show you in this specific case the benefit of ensembling only. So again, we consider a neural network and we assume that the likelihood is Gaussian. So what does it mean? It means that whenever the neural network predicts something, we assume that the location of predicts a position in the XY location of the device. We assume that the probability of that device position is modeled as a Gaussian distribution. We have seen before that if you use normal Bayesian learning, we usually obtain a degenerate solution. So we obtain a single model Gaussian distribution. And so in this case, since whenever you have RSSI-based localization, you cannot really pinpoint the location of a device, the true distribution of the device given the RSSI measurement is far from being unimodal. And therefore, if you commit to this model class, we are bound to be misspecified. And again, we can see the detrimental effect of misspecified models in this scenario, in which we have, now let me explain this figure. In this figure, we have the deployment area, we have the black dots representing the training samples, we have the green ball being the true location, and in shade of red, we have the density, the predicted density by the model after training. If you use the standard pre-energy, again, we obtain a single Gaussian model, which is uninformative. I mean, it tells you that the device is located here. We have never seen a device being here. So for instance, if this is a street, it tells you that the device is in the middle of it. Doesn't make any sense. However, if we use robust Bayesian learning, but in this case, using only ensembling, we see why this guy has failed, because the device, the RSSI vector doesn't allow you to pinpoint the device, but tells you that the device can be either here or here. And this guy here just predicted the mean of the two clusters being somewhere, somewhere in between of a field, let's say. Whereas if we use ensembling, we can obtain much more informative distribution and predict uncertainty much better. And this is very, very important, for instance, in localization, in which, let's say, you have to convict somebody based on the trace of this phone. And a judge knowing this information may make the decision-making process much more informed than a judge knowing that the criminal has been somewhere in the middle of the field. So this goes for misspecification and how we can counteract. Now let's look what happens if we have outliers. And what we see again is that in this case, we have 3 different data sets, real world measurements, and we contaminate the data set by by changing some location to random instead of being the true reported one. And again, we see that as we increase epsilon, which is the fraction of these anomalous data points in the data set, we see that the frequencies and the robust Bayesian learning with t equal to 1, so the one employed the log loss, have a very sharp performance degradation, while the one that we propose with even a small value of t, so 0.96, so just to make the log loss bounded, is able to have a much graceful degradation of its performance. So once again, we are able to counteract both, even in this scenario. Final case is about unsupervised learning, and we consider channel simulation. So we consider channel simulation using variational autoencoder. We have samples from some channel, and we want to train a variational autoencoder, which is a generative model that is then able to generate new samples from that specific channel model distribution. In this case, again, we consider a training set which comprises samples from the channel that we want to model plus some other outliers. So for instance, in this case, we consider a TDLA channel model with a delay spread of 100 nanoseconds as the target distribution, while we consider a TDLA channel model again with a larger delay spread as the outlying distribution. As you can see, the TDLA with 100 nanosecond delay spread is more as a channel response, which is shorter, while the one with a longer delay spread has multiple components that combine later on in future channel steps. So what happens in this case? Again, you can use the variational autoencoder trained using the Bayesian framework or the frequencies learning framework, and then you can use the robust Bayesian learning framework to check what happens in this case. And for this one, I give you first I give you the distribution of the output of variational autoencoder in case of frequencies learning, so not robust to outliers and misspecified model classes. And as you can see, this is the predicted distribution. And if you look here, we have the response, which is of the out of distribution, so of the outlier. So the frequencies learning. So if we train the variational autoencoder using frequencies learning, we are bound to model also the distribution of the outlier channel distribution. Whereas if we use robust Bayesian learning, we can get rid of it and just model the peaks associated to the TDLA with shorter delay spread. Now, if we go to objective metrics, what we do now in this case is a bit different. We consider different metrics. We consider the maximum mean discrepancy, which is a measure of discrepancy between the target distribution that we want to model, so the TDLA with short delay spread, and the output of the variational autoencoder trained with the robust Bayesian learning framework. Again, we have T on the x-axis, and we have the MMD, so the maximum mean discrepancy computed for the frequencies approach, which is again is constant because T doesn't appear in that criterion, and the 4T robust Bayesian learning. And what we can see is that for T equal to 1, T robust Bayesian learning performance and the frequency is 1. But however, if we decrease T, we can have a twofold improvement in its approximation capabilities, because as I show you in the few slides, the T robust Bayesian learning is able to filter out the taps of the channel with the longer delay spread. The second metric that we consider is the area under the receiving operator curve. That is an indicator of how well we can distinguish between the in distribution and out distribution. Out of distribution and in distribution, yes. And what we see again is that frequencies learning is not able to really tell apart these two distribution, while robust Bayesian learning, as T decreases, is able to actually become a perfect discriminator between these two channel models. And I think I didn't have time to prepare a conclusion slide, so this is it. And thanks.
Thank you for the question, Mark. I was wondering, in one of the slides, you showed that you used clean data for training. No, sorry, noisy data for training and clean data for testing. But I mean, to me, it sounds a little bit like, counterintuitive because usually in training phase, you have to control the environment. So you cannot in clean data set, but in the inference phase, since you don't have control on the environment, it's usually noisy. So can you elaborate?
I think this is true for a computer science application in which where people, checking every data point or having very controlled data generation procedure. But over wireless, you have just machine doing measurements, and that's it. So you cannot really control what you train on. And maybe this is true for paper. Whenever we work with data set, we have some people that curate the data set. But if you want these machine learning models be applied outside in the real world, you don't expect anybody to any human in the loop. You just have device. I mean, if you want really smart devices, they need to be smart without us. They need to be independent and autonomous. So we don't expect to have any kind of data creation performed by humans.
But then how come in the testing phase you have
because in the end you want to be able to do good prediction in the case in which your data follows I mean, if you want to do RSSI based localization, you want to locate the user that are really in that location. You want to add in your testing data some thresh points and be able to model also the thresh of the outliers. So you have a target distribution, which is the one that you expect your system to operate in under normal condition. Then you have this corrupted one, which is the one that you are bounded to train your model because you just collect the measurements and not really filter them out. But whenever you test your model, you don't want the model to perform well on outliers because outliers are rubbish.
So, can you go back to slide 24?
Yes.
Right. So clearly, I missed the difference between these two metrics, but I was wondering why the accuracy improves while T decreases towards 0.5, while you have an optimal point for the other metric.
Yeah, this is maybe the main weaknesses of this approach is that clearly there exists a best value of T. And this depends on the contamination ratio. So because T is the parameter that allows you to control the effect of outliers. And if there are no outliers, T equal to 1 makes all these models perform similarly. However, whenever there are outliers for T less than 1, you have this big performance scale because you see the calibration error goes from 0.12 to 0.2. So it's like 6 times smaller. And but yeah, so there exists a best T, but you can see that if you just take our solution, the best T lies in a very big range from 1 to 0.6. So clearly, it would be nice to investigate maybe based on maybe a fine procedure that, based on the training that you have, finds out which is the optimal T. So far, we can just show that for a large span of values, the proposed solution works better than what we have.
What I didn't get is why the accuracy improves if the error was increased.
No, but this is the expectation calibration error. So this is a different method. The accuracy tells you how good your model is at making predictions. Right. So let's say my model is able to tell when a cat is a cat or a dog is a dog. The calibration tells you how good is my model in quantifying the confidence of its predictions. Right. And so, for instance, if you have a model which is overconfident and is badly calibrated, it might make even 0.01% times an error, but when it makes an error, he's sure about his error. So you can have accuracy being 99%, but the expected calibration error being very low.
No. Right. Thank you.
I'm gonna be nasty.
Yeah.
So get ready. First, I think the results in this case are. I think you are not doing a fair comparison.
Okay.
First, because you could use the T loss function for the frequency learning.
Yeah, I think so. Yeah.
You could, given the result that you're having, maybe you could say, I'm going to use the T for the frequency learning.
Yeah.
And then maybe the same improvement because you're adding the misspecification that the frequency is incorrect.
Yeah.
So my first one.
Okay.
And the second comment is the frequencies has less complexity because you're only using one model while you're using four.
Yeah.
So you could, in general, people when they do neural networks don't want to use more than one model. Like just think that you're a Facebook and you give them this solution. So for every image that you upload, the computational complexity is 4 times.
Yeah.
So people don't want to use more. And most of the people that use Bayesian learning, the whole point is how can you do Bayesian learning with only one model? How can you adapt those things? And then the next thing is you use dropout in order to train the frequencies. And most likely you didn't.
No.
So all of those things will make the frequencies drop out just a lot in improving the easy. So the question here is why didn't you do a performance?
Okay. So first off, this 1T is a good approximation of the frequencies because we have seen that whenever you have m equal to 1, you have a very similar performance.
Let me put it that you use T for that.
Yeah, exactly. But this is like frequencies with T. So you can consider this one as frequencies with T. And I don't know if I have ever, if I've done it anywhere else. No, okay. Okay. But also here, yeah. No, this is with n equal to 10. So yeah, if this is not the case. But yeah, so I don't know why we scrap it off. I'm sure I had in many plots. I originally had the frequencies one. Maybe we didn't put in this one because we have this robust Bayesian with T, with n equal to 1 being a good approximation of the frequencies one. And the main catch there is that people use frequencies learning in wireless communication system a lot. And this goes also to motivate the complexity part because, as I said again, whenever we have to solve problems in engineering, we have many things to trade. We can have low complexity and low complexity and low calibration, but sometimes we are willing to trade computational complexity for calibration. Let's say for very important application, safety critical application, you're willing to make your hardware twice or 4 times more powerful or increase the delay whenever you have, let's say, to perform some critical decision, like, for instance, in this the usual example, but in autonomous driving, you want to be able to have confidence in detecting a pedestrian, which is reflecting the true uncertainty that you have. So in those cases, it's important to complement accuracy or computational complexity and trade those with calibration. Coming to the
that okay, they use a network that is 4 times as strong in this case.
but
maybe you can do better with the T robust is targeted to the change that we do.
Yeah, but for instance,
use a network that is 4 times as good.
but for instance, in this case you cannot. In this, for instance, in this case you can.
This is a different problem.
Yeah.
I'm complaining about the other one.
And the classification one.
This one I can complain.
Okay, wow. Wow, Shirin, you had a very tough time.
I said I was going to be the last one.
Yeah, okay. So, okay, but I mean, it would be nice to try, but I think that even if you make this thing 4 times, the frequency is 4 times larger, I'm not sure if you are able to improve the calibration that much.
You're getting the calibration to T, not to the 4 result. Just look at the calibration in 2070. 1 and 4 give you the same calibration. If you're looking for the best calibration that you can get.
Yeah, this should be.
No, between the red, you convince me that the red and the gray are the same.
The red and the green, yeah, at least for the optimal T, they perform well. Wow.
No, I mean, for you cheating.
Okay.
And because you didn't use the T loss or the base or the you're saying that the frequency doesn't work, and then the Bayesian does. When you just
Okay.
that the red and the gray.
I might say that in this scenario for classification might be the case that if you tune the frequencies properly, then you can obtain the same.
You should do that. You should tune the frequencies properly because that's the operation study that was missing here.
Yeah.
If you propose a new loss function, you should add the loss function, especially because you're adding the error in a way that the frequency is not. I mean, this is. I am very basic, so it's not don't let me answer, but you are doing exactly the thing that the frequencies complain about the basic, that you change the game in order for the frequencies not to perform.
No, okay.
So that's So you need to do in the comparison with the frequencies, you have to do it that part.
Okay.
Okay, and in this case, you are clearly cheating in that case because the red one is equal, the red one should behave very close to the frequencies. And my take is, if you want to do something that is very calibrated, as soon as you are dropout, you win a lot. Because
Okay.
dropout has created all these alternative paths that you don't go and overfit as much. So, so all of those things, you're in a way misrepresenting what the best frequency solution
Okay.
in this.
Okay.
In the localization, we can talk about the fact that I don't think,
Yeah.
But the other ones, I think you are playing to, or I'm gonna use a frequency model that is not tuned to the problem and what it means.
Okay. Okay. Thanks for the criticism.
Modulation detection, I'm listening for your idea, I'm not much sure. 70% accuracy, so at least 30%. Correct modulation.
Sorry, I didn't get the first part.
Yes. Like this, what is the baseline of a normal modulation detection that people use today?
All depends on the data you train on. I mean, on the SNR level.
Is there something in a mistake?
Yeah, but I mean, for a high SNR, you can go up to 100. I mean, this one I don't remember if I have written here. You can check this data set here. It goes from some low SNR to high SNR. So whenever you report this, you take the average over all SNRs levels, and for very low SNR, you cannot do anything because you have just noise and you cannot really tell apart any modulations from the other.
Just to see how far away neural networks are from their traditional.
I don't know. I think. I mean, this paper here, I mean, got a lot of citation because it does much better than the traditional one. So whatever you see for, I mean, what you see here probably is better than any handcraft modulation classifier that you do. I mean, by hand or but use some models using some statistics.
I guess theoretical benchmarks would be nice.
Yeah. No, definitely. That whenever that you have, for instance, in your training data, you have vector over 6 signal, which is the sum of 2 different modulation, and you have that the label of that signal is one of the 2 modulation that are superimposed, and that's not an informative sample because you have something which is does not behave as the modulation that you are supposed to predict. No, because it's tested on the clean data, so yeah. Okay.
Thanks a lot.
Can I?
You can leave now.
Yeah. Okay.
Goodbye. Can you hear me?
Yeah, I can hear you. Should I actually have my video on or not?
Yeah,
Okay, it's fine.
let me try to see if I can get the audio.
Oh,
Can you
okay.
talk again?
Can you hear me?
Anai?
Can you hear me?
Okay.
Hello?
We cannot hear you. Wait. Anai, can you talk again?
Yeah, can you hear me?
We can hear you perfectly.
Okay. Sure. I'll have my camera on if I can. Okay.
Okay. Perfect. So let me put the camera on. Good
Yeah.
to see.
Hi. Good to see you all.
Now, can you share your screen?
Yeah, let me see if I can share. Can you see it?
Perfect. Okay.
Okay.
So I looked as well, and I just decrease a little bit the volume of it.
Wait. The thing with decreasing the volume. Can you speak less louder?
Okay, I try to speak this a little bit softly then.
Let me. Yeah. Wait.
No worries, no worries.
Let's try again. Okay. And now you can try again.
Yep. Can you hear me now cleanly?
The problem with the volume. Let me try because Andrea wants to sleep over your tongue.
But I'm buying.
No, you get. Come again.
Can you hear me?
So everybody can keep on sleeping while you present.
Okay, I mean, fine enough.
I think that is important. When we finish, in order to ask questions, you have to come because the microphone is my laptop. Okay.
Right. Or maybe someone can say what that will be the question.
We have a volunteer.
Someone has to be a volunteer. That has to be the only way to do it. Anyway, shall I start then?
Yeah.
Okay, so sadly I couldn't be there to present this in person, but yeah, so I'm basically going to present essentially my summary of my entire work during the PhD. So essentially my analysis of different optimization schemes based on anticipatory networks for next generation networks. And obviously my supervisor, Professor Zanella, is the one who is more responsible for all the works that we have done together. So, okay. So just to briefly just list out the projects that I did during my entire 3 years was with respect to some of my colleagues in the project was the clustering mechanism that I did during my time in CDC. Then the routing strategies that we defined for FARNets and the beamforming work that also I did in collaboration with my colleagues from CDC. And lastly, the work that we did on capacity maximization in transport layer. So to give a small introduction on why my PhD or why my project was actually incorporated in this project, and essentially as a part of a PhD was essentially you have anticipation or anticipatory networks. So anticipation essentially is technology specific. So essentially you have to actually know which technologies you're using to actually define anticipation or predictive mechanisms, as well as you need to know which applications are actually generating the data to actually do a predictive mechanism. It also depends on a lot anticipatory information that has to be taken into account. Also depends on what kind of networks you're actually capturing the data on, such as wireless LANs or cellular networks. Has to be depend on the topology, so essentially geographical information, localization information, and so on. And also has to be depending on the user specific. So what kind of devices are actually there in the network that are actually generating such data for predictions. Now, using such information, you can devise different applications based on these predictions. So some examples being channel prediction mechanisms in wireless LANs or routing mechanisms in ad hoc networks. So the first work, or one of the initial later works that we did, was in collaboration with some of my colleagues from CTC, was in user clustering for rate splitting mechanisms. So in rate splitting, essentially what we considered was a more hierarchical rate splitting mechanism, wherein you have multiple users in the area that have to be served by a base station. this base station can serve only a maximum number of users depending on the number of antennas at the base station. So to actually maximize the capacity achieved, the throughput achieved at the users, you have to group users that actually can then take advantage of the rate splitting mechanism, which takes into account hierarchy of these groups and defines beamformers for individual groups and the users such that it minimizes interference between the users and between the groups. But to do so, you have to actually employ a more hierarchical clustering mechanism, which is iterative process. Essentially, you have to define each pairings of users and then define groups based on which pairings actually give you the maximum spectral efficiency or maximum throughput. So to simplify it, we defined essentially a neural network based mechanism that would actually have a supervised learning to actually cluster these users. So using the neural networks, we basically compared the performances achieved with the neural network and with the hierarchical clustering mechanism. Bear in mind, the hierarchical clustering mechanism is complicated than the neural network, and we almost got a very similar performance for all the different scenarios that we tested on. And the biggest advantage was with respect to the relative rate achieved for both mechanisms, for hierarchical clustering and for neural network, wherein the drop was at max 10%, which is actually pretty good considering that you are actually trading a lot of you're gaining a lot of complexity, gaining in terms of complexity. So this was one of the works, or a summary of work that we did with Solidity. Now to move on, one of the major works that I've been doing for the last 3 years was basically routing and FANETs. So essentially what FANETs, as a lot of you guys know, is essentially flying ad hoc networks, which are comprised of UAVs and that take into account that can be used for tracking and monitoring operations. And essentially the biggest challenge for such kind of networks is actually having continuous communication from the UAVs to the ground. So essentially all the UAVs might not be in the transmission range of the ground controller. So you have to actually develop an ad hoc network that actually can transmit and can communicate this information over the entire network to the ground controller and back. But doing so, it actually creates a very dynamic topology because of the mobilities of the UAVs and the ad hoc nature of the network. So it creates a lot of issues with respect to routing. So just to have a recap on what routing actually existed in FANET. So FANETs or MANETs, to put it in the general aspect, MANET protocols has been existing for the last 20, 25, 30 years. So the idea of FANETs or the protocols in FANETs have always been dependent on using the traditional MANET protocols. But the biggest disadvantage in this kind of scenarios is actually because of the mobilities of the UAVs, the uncertainty in the information. So essentially position information that is captured by the GPS is actually very it's actually very wrong. So there is a high degree of uncertainty in terms of the information obtained. So to do so, we devise a solution of such kind of a scenario wherein you offload a lot of computing information with respect to routing to the central controller through a long range control link such as a LoRa. So through LoRa, you can update the positions or the GPS positions to the ground controller, and the ground controller can then have essentially has a Kalman filter that actually tracks this position over a period of time, depending on the position updates and the accuracy of the predictions. Obviously, the trade-off is you have to actually, there is a predictive error that actually introduces in such kind of scenarios. So to handle this kind of a predictive error, we actually model this prediction error as a random variable, or essentially a Gaussian random variable that depends on the mobility of the user of the UAVs in the area and the direction they're moving in. So the biggest challenge in this kind of scenarios is taking into account this probabilistic model and defining routes uh, using these probabilities, and then communicating these routes over LoRa. So LoRa essentially doesn't offer you a lot of leeway in terms of communication with respect to how much you can communicate over a certain duration. So essentially the capacity or the throughput is actually pretty low. So that means that you have to devise all the routes in beforehand at the base station and then transmit them to the UAVs. So to do so, we actually define it on link existence. So essentially, whether the link exists between your UAVs. Now, in this case, there has to be a probability because you exactly don't know the positions of the UAVs. So you consider the probability as a combination, as a multivariate Gaussian variable, taking into account the positional uncertainty between the UAVs, I and J in this consideration. And using this link existence probability, we define an entire route probability. So the route probability essentially is the product of the probability of link existences. But this link existences are conditional with respect to the previous hops because they have a positional constraint with respect to each UAV that is common between two links. So this probability essentially has to be maximized to actually find a route that is almost optimal. But this route, the most optimal route can still have a probability that is pretty smaller in terms of existence. So to compensate for that, we actually take into account a little bit, take into account backup routes as well. So essentially taking into account the probability that a particular link fails in the optimal route, and you basically devise the probability of root existence for backup root existence given a particular link failure. Now, to just summarize some results on this kind of scenario. So we basically did it initially, and we actually computed this work. Hello. Computed this work, and the performance that we achieved, even for just considering one path, so even without considering the backup paths for such kind of scenario, was extremely good with respect to the current works. So this is the geographical protocol that is there in the literature, and just considering the simple average distance between the UAVs from the central controller. So essentially considering the uncertainty and the distance between the uncertainties. So this was more relevant, but the drawback of this kind of a work was you have to continuously update the routes from the central controller to the UAVs, because it has to be updated every single time. So to test the sustainability of these routes, we actually devise, rather than just considering the existence probability for only a one time instant, we consider it over a period of time. So essentially for t time instances, and then we compute the route existence probability as a average of these existence probabilities over a time period. Now, to actually compute the sustainability of it, we define two metrics, because the scenario being very specific with respect to routing, we consider availability time of the route. So essentially how much time the route was actually active and existing over the entire simulation. And as well as we also consider an establishment overhead. So essentially, instead of considering as a routing overhead, which is more of in a data channel, so essentially how much you're expending your data output or data throughput with respect to control information. Because we have two different channels with respect to data and control, we define it as a establishment overheads. Essentially the routing packets being the packets exchanged from the controller to the UAVs, and we consider it irrespective of the density of the network and the entire simulation. So to consider in the same scenario, we consider an upper bound. So the upper bound essentially is so the root essentially exists for sure. That's basically what you know if you have perfect information. So how good does the protocol actually serve when you have such a kind of a scenario? So in this case, the analysis shows that the protocol actually does pretty well with respect to the RIR. Obviously, it's only 50% in this kind of a scenario, but this is the median output for such kind of a scenario was 0.9, and as you increase the prediction window, it goes on decreasing as expected. After 10 seconds, the RIR goes way different. I didn't plot it here, but it goes approximately like median basically is like 0.4. So this actually shows that the routes that are actually defined by Smurf, the protocol actually works pretty well. We also considered it with respect to idealized version of AODVs, so essentially considering that AODVs can continuously update the network, irrespective of considering how much packets you're actually how much packets you're sending out in the network. So we also take into account the impact of backups in such kind of scenario. So when in a small prediction window, it was not very good to actually consider backups because it didn't give any advantage, but it started to give you more information, more of a gain when you consider a larger prediction window. Obviously, if you actually go much further, the median drops very further. So even if the advantage with the backups, the overall performance is actually pretty low. And with respect to the density as well, so we considered how much of density would have impact with respect to such kind of predictions. So when it was a small prediction window, especially with an upper bound that had as a low density, and the performance is approximately similar to distance and not very distance from the AODVs. But the more critical one was in the 5-second and the 10-second. In 10-second, actually the AODVS, so basically the protocol that actually continuously sends out routing updates for all the nodes in the network, performed much better than Smurf. But this was compensated due to the fact that the routing overhead that is achieved for this protocol was pretty high compared to Smurf. So there was a trade-off between performance and the overhead that is caused for such performance. Anyway, so moving on, so considering the same kind of scenario, we took into account what would happen if you actually considered not having a very omnidirectional static link, but having a more beamformed millimeter wave link for the network. So this was work I did with some of my colleagues from CDC as well. And in this work, we first started off with a very simplified planar array design for beamforming. And we defined the steering vector. We kept the beamforming design constant for all the UAVs, and we only defined steering vectors based on the angular deviation for the uncertainties observed in the network. And using those steering vectors, we defined the channel model and the channel gain. And because this steering vector is based on estimated angular deviation, we actually compute it as an expected capacity that is achieved by the UAVs over the network. And using this expected capacity, we actually try to maximize the capacity achieved over the network. So in this scenario, we actually consider both because beamforming is very dependent on the true positions of the UAV of the nodes. We consider the performance change with respect to tracked and true. So essentially, if there is an uncertainty in the positions and there is no uncertainty. With respect to density, it was pretty consistent for both scenarios. But with respect to beamforming, it was more critical. When it was true positions, the performance didn't change even if you increased the number of elements in the network in the UAVs. But the performance dropped heavily when we actually considered higher number of antenna elements. This was due to the fact that the performance is dependent on the beamforming have to be rightly steered towards the receivers. And if you have a higher uncertainty, and if larger number of elements allow you to have a minimal narrow beamforming, it tends to miss the receiver completely. So to actually take this into account, we actually devised a more adaptive nature for the beamforming design. So in this scenario, we took into account a full mathematical model for the angular deviation between the transmitter and the UAVs with respect to the angular deviation and the position or the distance between the uncertainties. And using this positional model, we actually define expected capacity for different angular deviations and different beam widths. Now, in this scenario, we actually keep it a more for code book to actually have a simplistic computations, but it will be more smoother if you actually have a continuous beamforming designs. Anyway, so taking into account, we actually defined two different approaches for the adaptability. So essentially considering similar approach as previously, where you actually maximize the capacity achieved over the route, and instead of actually and the second approach being, instead of maximizing the capacity, we maximize the probability that a certain capacity is achieved. Now, this actually becomes more relevant with respect to applications such as video streaming or in monitoring, because if you have a video stream that is of a continuous bit rate, it is much more necessary for you to have a continuous stable route, continuous stable capacity over the route, instead of actually having a very high capacity over a particular period of time and then reducing and having a drop in it. So the two approaches actually had their advantage and disadvantage on both sides. In the advantage part was when you have a small number of elements, the expected capacity actually worked much better compared to the probability one. This is due to the fact that when you have a small number of elements, the protocol doesn't have the ability to actually generate beamforming patterns that are narrow enough. So in a lot of scenarios, the chance of missing the receiver actually reduces, thereby actually allowing the protocol to choose routes that are directly maximizing the capacity. This obviously gets worse as it goes with increasing number of elements, because there is a chance that you actually then reduce there is a chance that you might actually miss the receiver if you consider a narrow beamforming, even if your expected capacity was higher. This also was relevant with respect to density, because if you consider density always determines how variant your performance is going to be over the network. If you have a higher density, you have a very less variance in the performance. But the biggest criteria was when you have a small number of elements, the density actually allowed the performance of increasing the density actually increased the performance over the period over the densities. But as you increase the number of elements, it actually decreases much further. So in such scenarios, expected actually the JBRE, so expected capacity, actually performs well when you have smaller number of elements. But if you have larger number of elements, it's much better for you to use probabilistic capacity. And a much more relevant criteria in this kind of scenario was the worst case scenario capacity, so 5th percentile capacities. So in this case, the probabilistic mechanism was much more relevant. So if you actually want to guarantee, even in the worst case scenarios, a particular capacity, the probabilistic mechanism performs much better than the expected capacity. irrespective of how many elements you have. And lastly, presenting one of my works that we did basically in collaboration with King's College London, was a scheduling mechanism for transport layer. So essentially taking into account QUIC. So QUIC is a protocol that actually contains multiple streams which transmit data over a single channel. The advantage of QUIC is if you lose one packet, the connection is not blocked. On contrary to TCP, which is the current protocol that we a lot of times we use, is if you lose one packet, because it's a byte stream that is sent over the entire channel, till the time TCP receives all the packets in, all the next packets are actually blocked. So essentially the head of line blocking problem. So this was more relevant with respect to tactile and with respect to vehicular information, wherein you have cameras that are actually transmitting information independently of each other, with having some correlation between each other. This is the correlation that we actually took into account to actually maximize the value of information at the other end. So essentially choosing a scheduling mechanism such that the data from all the sensors that is sent through the channel actually maximize the whole information instead of just maximizing the throughput, which is what you do in TCP. So essentially for vehicular sensors, we actually considered the value of information, and we devised 3 different mechanisms to actually analyze the importance of such value of information mechanisms. Just for note, the value of information metrics that you see here are actually from empirical values. So this VOI basically, so essentially when you consider both cross-sensor correlation and the value of information for all the packets that are sent out, the performance was the best when you consider both scenarios while scheduling the packets. This was slightly less relevant with respect to tactile or haptic sensors, because haptic sensors essentially don't have a cross-sensor correlation between each other, so they are independent of each other. All of these sensors are independent of each other. So essentially, it comes down to how long it has been for the sensor data has been transmitted to the receivers. So in this scenario, we actually consider it as a quality of experience. So essentially, if you move your finger, how long does the other end would take to actually respond? So just to give a final thoughts on the entire work that we did. So why this work was relevant with respect to my PhD? So this work was relevant with respect due to the fact that we actually defined more predictive analysis on optimization schemes over a wide system for the next generation networks, such as drone networks. So essentially, it becomes highly relevant to actually do such kind of analysis in the future as well, because it is necessary to evaluate different criteria and different protocols for different application scenarios with respect to different information available. Thank you.
I promise I'm not going to put your questions.
What?
Hi, and I.
Yeah, hi.
I'm just, relaying, thank you, questions from the audience. Any questions?
Yeah.
On line 12.
Slide 12.
Slide 12.
That one. The next one. Good.
Oh, this one. Okay.
What is the NPGR?
Yeah.
This one.
Yeah, that's right. And I.
Sorry, what?
Yeah, that was the question. So in general, you use a number of acronyms in this presentation, so it's very difficult to follow.
Yeah, so MPGR was a geographical protocol that was there in the literature. So
it's another protocol taken from the literature. Long story short.
It's like the Bayesian. Say again?
It's like a baseline that you are comparing.
Yeah.
Yeah, exactly, like a baseline.
Is there any reason why it performs so like from 0% accuracy to 100% accuracy? That was my main question.
Yeah, so the performance for the so the biggest weird and the weirdest aspect of this kind of analysis was because if you're considering geographical protocols, they are a lot of times they are very greedy, so they are trying to maximize the next hop. And if you do not have a particular idea of where the user or the UAV is in the network, the uncertainty can cause the performance degradation quite heavily. That's the reason why it is so huge.
But maybe, and you should explain which kind of plot it is. That's a box plot. I didn't
Oh, it's a box
that.
plot. My bad.
Alright.
Yeah, my bad. It's a box plot. So it essentially shows the variance between the performance achieved. So yeah.
Right. So do you have any other technical questions? Otherwise, I have some comments regarding the presentation. No other technical questions. So in general, and I tell this to you, but hopefully might be something useful also for your mates.
Yeah.
So when you present something, it's good to, to set clearly the background. For example, when you compare the performance of the protocol that you propose with some baseline, would be nice to describe the baseline in order to what's the main difference, right, between your protocol and what's already there in the state of the art. As I said, you present a number of results with tons of acronyms. I believe it's basically impossible to understand the different curves. I've been collaborating with you, and I can't follow you when you present.
Yeah, I mean, I tried to summarize it as much as possible, but I think maybe I should reduce it a little bit more with respect to the acronyms and everything.
Yeah, you should try to focus on the main lesson learned. If time is short, you cannot present every single detail. So
I
think is to provide a general vision, a general idea of what you have done and why it performs better than the literature, if it does perform better than the literature.
Yeah.
In particular, the work with beamforming, this is something that we discussed multiple times, and I keep forgetting the conclusions of these discussions. But go back a few slides. Again.
This one?
No, previous one. The first slide, right? This one.
This one, right?
Yeah, right. Here you have the number of antennas on the x-axis and the average throughput on the y-axis, right? And you compare these different versions of the protocol that you define. BA stands for what?
So BA is the beam aware. So essentially the beam aware part of it.
All right. While DBR
is the distance protocol. I think I kept it as consistent with it, but okay, yeah, I should actually said that here, but yeah, that's my part.
Yeah, this is a good idea. But I was wondering why you said that by increasing the number of antennas, basically, which means that you consider narrower beams.
Narrower beams, yes.
So the performance decreases, and the performance decreases for at least two algorithms here, two protocols.
No, for all three, actually, it decreases for all three.
Three protocols, right? Because the position uncertainty makes the beam alignment more critical, right? So you might have some disalignment in the beam pointing.
Yeah.
Good, but what's the advantage of having narrower beam? Usually you increase the throughput, right? So
correct.
Or you increase the distance, one of the two, right? And
so this is exactly the trade-off. So essentially, it's the trade-off between the distance, power. So in this case, and obviously we keep the power constant. So distance changes with respect to the uncertainty then. So distance becomes more critical. So if you have a very smaller distance and a narrower beam, and if you have a very higher uncertainty, there's a higher chance for you to miss the beam, even if you are considering
we don't see any trade-off, right? So you see that in some protocols you have a performance loss because of the position uncertainty makes the beam alignment more critical, but you don't see an improvement in the throughput in the other cases where maybe the beam alignment is easier because the uncertainty in the position is lower. So I don't see, for example, that the maximum throughput is constant. You don't increase it, right? For any protocol.
So the maximum throughput is essentially this is the throughput. So this is a minimum throughput achieved for over the network. So essentially for a Monte Carlo scheme on a Monte Carlo analysis, the minimum throughput achieved for over a route. That's the reason why the overall throughput actually, or the average throughput actually goes down. I was clear about it. Maybe I'm wrong.
Mm. Again, all right. I discussed
No,
it
so
once more with you in previous.
I mean, so the point was actually to actually evaluate on does this actually is useful or not. But it actually doesn't provide any usage when you actually increase the number of elements for any kind of a scenario. That's the reason why I actually considered, instead of keeping the beamforming constant, we actually vary the beamforming, which is what we can do if you actually have the antenna patterns or the antenna design fixed on the UAVs, but you vary the beamforming design. So essentially compute digital beamformings based on the uncertainty that is actually visible or observed by the controllers.
All right. Oh.
Yeah. If you apply it blanketly, it doesn't give you any use, basically.
So, but basically, given a certain number of antennas, the beam width is fixed in this analysis, right?
Exactly. Yes, the beam
So
width is fixed.
it might be better to somehow write something related to the beam width and the x-axis, because if you have multiple antennas, you are not really obliged to use all of them to have a narrow beam, right? You can also decide
Correct.
to use a
Correct.
wider beam. So
Correct.
these are the performance that you get when you use all the antennas you have to realize the narrower beam that you can do with those antennas,
Yeah,
right? Okay.
Yeah.
All right. Any other question, please?
Yeah, maybe when we have this thought, you maximize the minimum expected throughput, right?
Sorry, I couldn't hear.
What is the explanation and what is the reason to have that minimum?
Do you have the question, Manai?
No, I cannot hear clearly. That's why.
So the question is, why do you choose to maximize the minimum expected throughput over the network rather than the average throughput or something like that?
Oh, so this is actually so essentially it's maximizing the bottleneck capacity in the network. So in the route, the route capacity is dependent on the minimum capacity over the entire route. So essentially the bottleneck. So how if you choose a bottleneck that is very low, your entire capacity, irrespective of other individual link capacities, your entire route capacity is dependent on the bottleneck. So that's basically why we choose to maximize the minimum expected capacity over the route.
But do you have there is some application in mind where it's really needed, this minimum capacity, or is it what nice thing to have? Maybe, but just wondering, because when you take average, maybe the spread is also
This is a good point.
Can you repeat?
Yeah, sure. The question is, do you have any application in mind that might benefit from an average minimum capacity above a certain threshold, considering that it's an expected capacity, so the actual capacity might be very, variable around this mean?
Yeah, obviously, like as I mentioned, so if you actually try to maximize the average minimum capacity or average minimum expected capacity, the applications such as video streaming for such kind of scenario. So in monitoring, if you have a video stream that you have to actually transmit over the entire network, if you actually have a higher capacity, it is actually much more higher minimum capacity is much more relevant or much more useful, basically, in that scenario. So that is one of the applications that we thought of when we did this work as well.
So he's saying that I'm also, reporting on the way back. Yeah, video streaming is one of the applications that requires a certain minimum capacity. But the question was, Anai, that if you consider the expected minimum capacity, so you're not providing any guarantee, right? So if the expected minimum capacity is 2 megabits per second, it doesn't mean that you have 2 megabits per second for the entire video streaming duration.
Correct.
But also the video streaming is not constant bit rate. So it's one metric. If I'm not wrong, in one of the other results, you report the percentile, right, of the throughput or something.
Yeah, so in this basically, so we basically extended the same work. So in this basically we actually considered the beamforming as adaptive and then computed the percentile on this then. So essentially the worst case scenario output or worst case scenario capacity achieved.
And here you have another set of very nice acronyms that I can understand what they mean, but still.
Yeah. I mean, I tried to keep it as small as possible, but yeah, that's
what
my
is not
bad.
really clear, Anai, is
Yes.
what is your proposal and what comes from the literature, right? So it is not clear if you do better or worse or similar to what is already there. So, for example, the GBRP protocol.
So these are the GPR. So essentially GPR are the ones that we designed in this work.
All right.
Although so we considered the baseline as still the Smurf and distance, which we did at the start. So
so you improved
essentially
over your previous version of the protocol, right?
Yes.
All right. Other questions, comments? Fine. Thank you, Anai, then again.
Thank you.